Hey guys, welcome back. In this video we want to calculate the strain energy buildup in this cantilever beam when we apply a 10 kilonewton point load to the end of it. So this is the formula that we've been using in the last couple of videos. We have strain energy divided by volume gives us a strain energy density. Strain energy is in units of joules, and so strain energy density is just joules per meter cubed or some variation of that. We derived this part of the expression in the last couple of videos, so we have the sigma x squared over 2e, and basically what we want to do is we want to use this expression to solve for u. Alright, so in order to solve for u, we are going to have to take the integral to get all the volume in there. So we take the integral of the left-hand side, so sigma x squared over 2e, and we are taking that with dv. Alright, what we can do, if you remember from the older videos where we talked about bending, we actually have sigma x is equal to my over I, where m is the internal moment and I is the moment of inertia for that cross-section. So we can substitute that in for sigma x. Notice it's squared there, so we're going to have this integral here. We'll have m squared y squared over 2e I squared, and that is still dv. Now we want to get away from dv here because that's just going to complicate things, and we do have a uniform cross-section along the length of this member, so what we can write is we can substitute dv here for dA dx. Alright, so when we make that substitution in our expression up here, we're going to have to change this to our integral going from 0 to L, and then we will have m squared y squared over 2e I squared, and we'll just rewrite this as dA dx. Okay, so when we look at this, m squared over 2ei, sorry, that's 2ei squared. M squared over 2ei squared is all a function of x, but we're having this y squared dA here kind of throw us off, so we're just going to rewrite this a little bit and pull that out. So we'll have, so from 0 to L, we have m squared over 2ei squared, and then we'll just throw this in brackets here. So we'll just have a little integral sign there. We'll have y squared dA and dx. Cool. Well, it turns out also, if you remember from previous videos, that the integral of y squared dA is equal to the moment of inertia. So basically this all can get crossed out with and replaced with an I, and that's going to cancel with one of those down at the bottom, and we can rewrite our expression for elastic strain energy as the integral from 0 to L of m squared over 2ei dx. Now this is a bit of a simplification. We are neglecting the effects of shear, and this is just the elastic strain energy due to bending. You can add in shear, but the purpose of this video is just to talk about strain energy due to bending, so we're just making that simplification, and this is the expression that we're going to be using. So again, just watch out, we're neglecting the effects of shear there. But when we look at this m squared up here, m is actually the equation for the moment in terms of x. So unless you're in pure bending, this expression won't be constant. We could write, like m of x, but I don't really like doing that because I'm going to get confused about whether or not that's an x term or the expression including x. So what we need to do now is we need to go ahead and find out a little bit more information. We're going to need to find the moment of inertia for this beam here, and we're also going to need to find the expression for m in terms of x. So maybe let's do moment of inertia first. We have I is just going to be equal to 1/12 base height cubed. So if we just throw all that in, we're going to get 1.28 times 10 to the negative 6 meters for. And to find the expression for moment in terms of x, we'll need to draw the free body diagram with a virtual cut in it. So we're going to find the internal shear here is just going to be equal to negative p, and then that means that our moment is going to have to be equal to negative p times x. So this is our expression for m that we're going to be plugging in. So let's go ahead and do that. Let's grab this expression and we'll work our way through. So we have our strain energy is equal to the integral from 0 to L. When we plug in m squared here, we're going to have on the top, we'll have negative p squared x squared, and then on the bottom we have 2ei. So what we can do is we can pull out negative p squared over 2ei is all constant, so let's bring it to the outside, and actually negative p squared, the negative sign is going to drop out of that, so we will just have p squared over 2ei times the integral from 0 to L of x squared dx. What we can do is we can do that integral here, so we have p squared over 2ei, all the constants stay the same, and this integral is just, we'll raise that, we'll do 1/3 x cubed, and actually this is from 0 to L, so we can just replace that x with an L. So 1/3 L cubed. Okay, we'll just simplify this. So let's just fill in all the numbers that we have. Alright, let's go and start canceling out units. We have 2 meters here, so that's going to go to 2. We have 3 meters up top, so that's going to go down to 1 when we cancel that out. All that's gone. Now when we cancel this out, be careful with where your brackets are, because we still have to cube the 0.5, right? We've just reduced the units here to 1 meters. We have 2 up here for newtons, so we can drop that. So we just have 1 newton on the top, and again, don't not square the 10,000, so don't forget to keep that in there. So let's just write this down here a little bit cleaner, making sure we have all of the proper units. So we have 10,000 squared newtons times 0.5 cubed meters, and then on the bottom we're going to have 6 times 200, and then when we have 10 to the 9 times 10 to the minus 6, we can just simplify that to 1,000, and then times 1.28. So there's no units on the bottom, the units on the top are newtons times meters, and that's good. That's going to give us the units that we expect for joules. So if you just put this in your calculator, we'll find out that that our elastic strain energy U is going to be equal to 8.14 Newton meters, and we can rewrite that as 8.14 joules. So there you go. Let's put a nice little box around it, 8.14 joules, or 8.14 Newton meters, and there we go. We've calculated the elastic strain energy in this rod once we've applied this point load of 10 kilonewtons.